Welcome back to the Experimental Math Seminar of Rutgers University. Today's speaker is our own Professor Volodya Retakh, who will speak about non-commutative integrable systems and Catalan numbers. As usual, please mute yourself.
Okay, all right. So thank you very much for the invitation. So I'll try. Okay, so let me start with the chain of differential equations. Later I will consider another one, but this chain is called Volterra chain or Lotka-Volterra chain, and it's written like this. So so you have a sequence of un, u sub n, and un prime can be written in the, in such a product. And there are different ways to look for solutions of this problem. Actually, so I was doing this in one of this paper, but it's more than 25 years ago. But so Adler and Shabbat, they suggested the following approach. Again, everything is commutative, so you have actually two determinants of this Hankel matrices, or well, call it Vronsky matrices, and one which starts with f, with the function f, and another one that starts with f prime. And then you can get solutions of these Volterra equations by this formula. So u1 is w1 over w naught. So this is just f prime over f. Then you have w2 over w1, and in general you have more sophisticated formulas, which in fact is more natural if you are writing its non-commutative analog, but we arrived to this. Okay. Okay. Now you're attempting the following. What kind of this function f you will choose? One of the way to choose is just to choose f as an exponential generating functions for Catalan numbers. Then the nth derivative of f at 0 will be just Catalan numbers. And we know properties of Catalan numbers, that the corresponding determinants, so these determinants, the value of the determinants at 0 are just 1. This is actually, so if you put, instead of f, you put C naught, then you put C1 and so on, and for the second determinant you start with the C1, then they will be equal to 1, and this is actually a characteristic property of Catalan numbers, so they can be defined in this way. So if you then, it immediately follows that if f is exponential generating function, which is written here, then just the initial solutions for functions un, which we use for Volterra system, Volterra chains, this initial condition just that they equals to 1 when n greater equal to 1. And conversely, if you have this initial condition, then f is the exponential generating functions for Catalan numbers. Okay, then you have like two temptations. One temptation is that you take the encyclopedia of integer sequences. write, they are exponential. For each sequence, you write it exponential generating function and try to see what kind of solutions you will get for this Volterra chain. And another temptation is to consider just non-commutative analog. So I will start with the second temptation. So now we'll let A be differential algebras, which means, it means that there is a linear map called D called the derivation, and the definition is that it must satisfy Leibniz rule. Then you can write you can solve a non-commutative Volterra chain, but you have to be very careful with those products. So it's better to write this as it's written here. So un plus 1 times un, and then minus un times, so it must be un minus 1. This is a misprint. N minus 1. Okay, now if in the non-commutative case you cannot use a general determinant, so you use something instead of it, which is called theory of quasi-determinants, which I recall now. I did it several times in this seminar, but anyway. So the definition is like follows. So you have you have n by n matrix over an associative ring. Then you define its submatrix when you omit ith row and jth column. And then you take the row R sub I, and this is the ith row, but without aij, and then you do the same with column. And you are writing the formula that is written here. Okay, now it looks rather ugly. My justification is that it's a useful expression. So let's see examples. For example, if you have 2 by 2 matrix and you want, say, to write, so to put I and j equals 1, then you have A11, then you consider the first row without A11, this is A12. Then if you cross first row and the first column, you have just A22, so you have right A22 minus inverse, and then you have the first column with A11, this is A21, so you have just this expression, and you can write in general 4 other expressions as they are written here. Now the advantage compared to the commutative case is that you may think about Aij as, say, operator, some morphisms from ith object to jth object, or you think about directed graph and Aij corresponds to just to the edge going from I to J. All right, now then if the inverse of A is defined, then there's clear connection between elements of the inverse matrix and this quasi-determinants, and in the commutative case, this quasi-determinants, this is just up to a sign, a ratio of the determinant of n by n matrix to the corresponding determinant of n minus 1 by n minus 1 matrix. Okay, now the notation is, so you can specify your index, indices just like this below, but sometimes it's convenient just to write this with boxes. Okay, now I will show you solution of the non-commutative Volterra chain. So I consider them quasi-determinant. So this is the first matrix is like in commutative case, but it's quasi-determinant. So I must have a boxed element, and I will take this, just the element which is to the right in the last row to the right. And I will do the same as with the other metrics. So in commutative case, Z sub n is just the ratio of Wn over Wn minus 2. Okay, and then the theorem is just the following, that U sub n is just this fraction, left fraction of these two quasi-determinants. And this gives you solution of this Volterra chain. Here it's written actually in the correct way. Okay, now why this is how it correlates with the commutative case? Well, in the commutative case, it gives you the following solution of U sub n. And so the first fraction times the second fraction taken with the inverse, and you have exactly this solution that was given by the commutative case. So at least now for me it looks more natural. Okay, now then, of course, then you would like to consider so this F involving in this matrix as this F as a exponential generating function of some non-commutative combinatorial numbers, and so we will do it now. And this thing is the following. So you consider now F as you consider just a series with non-commutative coefficients of this is, and T is the central variables. Then you define its derivation, and then you consider F as a exponential function, exponential generating function, but for non-commutative Catalan numbers. So now let me remind you what are non-commutative Catalan numbers. Again, so if you, just let's look at this expression, this quasi-determinant. In the commutative case, if C0, C1, and so on are just classical Catalan numbers, it must be equal to 1. Because it's the ratio of two determinants, each of those determinants is equal to 1. But I prefer to use free non-commutative variables, so just to say that this quasi-determinant must be equal to just a free variable, and the same with for the quasi-determinant which starts with a C1. So just this. Okay, now in both cases you have some rational equations, but we are lucky because the solutions are just rather simple polynomials. They are Laurent polynomials. So C0 is X0, C1 is X1, C2 is the first sum when you have an inverse. This is C3, and so on. And it's quite easy to write the solution because, first of all, you consider those words, and in these words, so you have powers are alternating from 1, -1, 1, -1, 1, -1. Also, each monomial starts with the positive power and ends with the positive power. And if you consider sum of indices for positive, sum of indices for positive powers minus sum of indices of the negative powers, you have just exactly the number of your Catalan, this Catalan number, or I don't know. Well, here, of course, number, to say that the non-commutive Catalan number, this is probably not exact word, but okay, but I will use it. So, and then you can write C4, and for example, and have like sum of 14 monomials, and so on, so on. There is also just a combinatorial description of this, and the combinatorial description looks like this. So you consider paths from just on a plane with integer coefficients from 0, 0 to N, which lie just below the diagonal. Well, this analog of Dick paths and so on. Now, if you have to each point on the plane P1 and P2, you associate its content, so the difference of the first coordinate by the second coordinate. This difference for our paths will be always greater or equal to 0. And each such path is characterized by its corners, so where it actually makes some where it change its direction. So for each of this corner of such corner corresponds, this is if this is variable x with a number. This is equal to content, so P1 minus P2. And then you have to assign just degree 1 or degree -1. And degree 1 is when you go to the right and up, and degree minus when you go first up and then to the right. For example, if you look at this, so this is C2. So you have actually paths from 0, 0 to 2, 2, and one path goes from 0, 0 to 2, 0, and then up, and this is x2. And another one goes, so one step to the right, then up, then one step to the right, then up. And so the first corner is just at the point 1, 0, corresponds to x1. The next corner has coordinates 1, 1, but it's obtained by going up and to the right. So this is x0 inverse, and then the next is x1, and so on. So you can do this track. Okay. And now, so you have these monomials, and actually this is your Catalan numbers is defined, can be defined like the sum of these monomials. And then we immediately have a solution of the non-commutative Volterra chain. So what are initial conditions? And the initial conditions are just the ratio of x sub n to x n minus 1, just this one. So now if you take, now you may consider a specialization of these non-commutative Catalan numbers. In fact, there are Catalan numbers which depend on two variables, q and c, so cqt, and cq1 can be obtained from our non-commutative Catalan number by this specialization. And in this case, the initial solution would be u sub n 0, it's just q n minus 1. So this is just quite a natural way to assume this. Okay. Right. And now I would like to go to another sort of chain. And in the commutative case, it's called Toda chain. So that's it came from physics. Let me do not explain why. And this is basically, it can be written like it's written here. So, but so more complicated than this Volterra chain because we have the second derivative. But surprisingly, it has actually the solution here is much simpler. And here is a solution. You just take this determinant. You do not need shifted determinant of shifted matrix. You just have this determinant. Now I put this in name of Sylvester chain because actually I read that such equations were known to Sylvester or to Darboux, because that's actually a very natural question. You take function, you consider this matrix, you consider determinant, and you ask what are just differential equations for this determinant, and this is just, you get these expressions. Okay. You may try it by yourself. Now, in non-commutative case, actually, you need to rewrite this and introduce just the ratio of this is tau n to tau n minus 1, it's written. And then if you just, after just very easy manipulation with the logarithmic derivatives, you have this notion. So here in the left, you have basically a derivation of a non-commutative logarithmic derivatives, and in the right, you have the difference of two ratios. Now, actually, non-commutative solution. So this was obtained just long ago, and it's actually again this is just this quasi-determinant. Okay, so later, so it was generalized, but so far. But okay, but if you have the solution and then you take f to be again exponential generating functions for non-commutative Cn, and then the initial solutions would be just equal to this type of just to these free variables. At that time, when we wrote the solution, we had no idea that one can use generating functions f. We just wrote this in general. Okay, now again, there is a temptation to replace to generalize these Catalan numbers. Especially this is easy for this Toda type equation because the solutions is simple. Okay, and now the definition of generalized Catalan numbers actually can be done like this. Suppose you have an infinite matrix over a ring, then you take its power and you take this upper left elements and you call it nth Catalan number defined by matrix A. Now, actually, the idea actually belongs to Aigner. So Aigner considered sort of only three diagonal matrices with this upper diagonal and lower diagonal equals 1. But he noticed that if the main diagonal looks like 1, 2, 2, 2, and so on, then you get Catalan numbers. If if your main diagonals consist just of ones, 1, 1, 1, and so on, then you get Motzkin numbers. Okay, now also that Aigner showed that if you then consider, in his case, these determinants of matrices that's written here, then this determinant will be equal to 1, so which is actually not surprising. Well, however, if you want to work with a non-commutative case, and you just assume that all entries of your matrix are just, say, free variables, then what you get is actually, you get just this, such a product, which again has a categorical meaning. You go from 0 to 1, from 1 to 2, and so n minus 1 to n, and then you go down. If all these guys are equal, all these variables equals to 1, then you get 1. So this is, but when you have this expression, of course, it's very easy to write interesting, rather simple initial solutions for Toda equation. So this. Okay. Well, as I said, so if f is exponential generating functions for these Catalan numbers that are defined by the three diagonal matrices, then here you have the formulas for initial conditions, and they will be just some nice monomials for just in these variables I plus 1. Okay, now then you probably want to okay. Okay, now then you want probably to try shifted Catalan, shifted Hankel matrices. Okay, because it's what we need for Volterra chain. And here, the answer is not so, it's less simple because you have to do the following. So you consider just squares n by n submatrix of your matrix A. were this. And okay, no, okay. So and you have the product that we had before, except that in the middle you have this quasi-determinant, so of this three diagonal matrix. Okay, and again, if you want to write nice initial conditions, so you have to just somehow to include these numbers, these quasi-determinants of these n by n matrices. Well, again, in the Catalan case, you would be lucky. In other cases, you wouldn't be so lucky, but maybe you do this. All right. So what I can, but anyway, so let me maybe return to the first just commutative situation. Sorry. Mhm. Okay. 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 So this is just a solution of this, well, classical Volterra equations. And I don't know if somebody can make experiments with a gain, with when f is generating exponential generating functions of some interesting sequences. So if you can program this and see maybe something interesting will come out of this.
What if we get the Motzkin generating function? Do you get anything interesting?
I did not try. One definitely. So these determinants W2K will be equals to 1.
Yeah.
But the other I don't remember now
Interesting.
what it is for Motzkin. Well, definitely some integer, but I don't remember.
Yes, it's a good way to generate new integer sequences from old ones. That's very good. Nice.
Yes. All right. And so, okay. So, and maybe I will stop now. So I was scared by this time limit.
Thank
So,
you.
so I,
Thanks so much. It's better to err on the low side than the upper side. Thank you much. And we have time for questions. So this is really very interesting, all this non-commutative theory. So maybe Matthew, do you remember, can you implement non-commutative calculations? What you did way back? Do you think you may be able to?
Yeah, I'm trying to remember everything that I did. So the two things I remember was number one, I remember to do the experimentation, the conjecturing side of things.
Yeah.
I used 2 by 2 matrices with integer entries with determinant 1 to kind of be my variable,
Yeah.
and so that just kind of let me know, because that, like to make sure I'm kind of satisfying the Laurent phenomenon. I don't want to want to make sure everything still has integer entries, even if I'm
Right.
surprisingly divided by stuff. But I did have some, I was able to teach Maple to do some simplification of, here's a string of non-commuting variables that follow some rules, and I was able to teach it to manipulate, put it into some canonical form. So yeah, I mean, that's the sort of stuff certainly.
Yeah, so maybe the same techniques might work here. You think?
Yeah.
So Volodya, even for the commutative case, probably you can get interesting.
Yes, yes. This is so. I decided just to show this in this seminar. So
Yeah,
maybe then I don't know, somehow of outside ideas from these
yeah,
differential equations.
yeah. Right. So nice how it's discrete. So it's recurrent and differential equations combined, and yeah, and the solar lattice is something famous mathematical physics. So it's interesting how it came up.
Yeah.
That's very interesting. But and this commutative interpretation of the non-commutative Catalan numbers in terms of weight enumerators of some paths. Do you have it for more general paths like Motzkin paths and even more general?
There are. So just so that I hope that we will finish this soon, and this is just a joint paper with Arkady and Misha Gertman, and it should be there.
Ah, interesting. Other question to Professor Retakh, Vladimir? Well, thanks so much for coming, and we see you in 2 weeks. And happy holiday. Bye, everybody. Thank you. Thank you.
Bye.
Bye-bye.